Have you ever just looked at a simple light bulb, one powered by a little battery, and thought about what's really going on in there? It seems so basic, right? But it's actually a doorway into this incredible hidden world of physics. So today, we're going right down that rabbit hole to see what makes that little light turn on.
So our whole adventure starts right here with something you've seen a million times. A battery, some wires, a switch, and a bulb. That's it. But inside this simple loop, there's a whole drama playing out, a story that follows some of the most fundamental rules of the universe. The big question is, how does this little loop actually make light? Well, the story of any electrical circuit is really a story about three main characters. There's a push that gets everything moving, a flow of energy, and some opposition that tries to slow things down. If you can get a handle on these three ideas, the whole thing just clicks into place. So let's follow the flow and see where it takes us. All right, first things first, let's get properly introduced to our three main players in this story: voltage, current, and resistance. Okay, first up, we've got voltage. Think of voltage as electrical pressure. It's the push from the battery. A great way to picture it is like the water pressure in a garden hose. The battery provides the force that's ready to get the electricity moving, and we measure this potential push in a unit you've definitely heard of: volts. So if voltage is the push, then current is the actual flow. This is the electricity on the move, the stream of charge that's actually zipping through the wires. Current tells us how much electricity is flowing past a certain point every second. We measure this flow in amperes, or as most of us call them, amps. And our third player is resistance. Just like the name says, this is the opposition. It's kind of like electrical friction. As the current tries to flow through that super thin little wire inside the light bulb, the filament, it meets a ton of resistance. But here's the cool part. This opposition isn't a bug, it's a feature. That struggle, that friction, is exactly what causes the filament to heat up and glow. It's the whole point. And we measure this resistance in a unit called ohms. So we have the push, the flow, and the opposition. But how do they all relate to each other? Well, it turns out there's one beautifully simple rule that governs their entire relationship. It's the law of the land for circuits. This is it. This is the golden rule, known as Ohm's law. It's so elegant. It just says that the voltage, the push, is equal to the current, the flow, multiplied by the resistance, the opposition. That's it. It's this perfect little mathematical relationship. If you know any two of these, you can always figure out the third. This simple equation is basically the blueprint for everything that happens in our circuit. And speaking of blueprints, this is what our circuit looks like to an engineer. It's called a schematic diagram. You can see the symbol for the battery, which is giving us that 1.5 volt push, the switch, and that squiggly line representing the bulb, which is providing our resistance. Now, let's put our new rule to the test. Let's say we have a 1.5 volt battery, and we know from our previous measurement that our bulb draws a current of 0.3 amps. We can rearrange Ohm's law to find the resistance, so voltage divided by current gives us resistance. That's 1.5 volts divided by 0.3 amps, which gives us a resistance of 5 ohms. See? Easy. And we're going to use that 5 ohm number as we move forward. Okay, so a single bulb is pretty straightforward. But what happens if we add a second bulb? This is where things get really, really interesting, because as it turns out, there's more than one way to wire it up. We've got two main options here. On the left, we have what's called a series circuit. See how the bulbs are in a single file line? The electricity has to go through the first one to get to the second one. On the right, we have a parallel circuit. Here, the path splits, kind of like a fork in the road, giving the electricity two separate branches to flow through, one for each bulb. Now, this difference is huge. In that series circuit, the bulbs are forced to share the path, which also means they have to share the voltage from the battery. But in parallel, each bulb gets its very own direct connection to the battery. That means each one gets the full 1.5 volts. And this one little difference completely changes how bright they'll be. So now we can use our superpower, Ohm's law, to actually predict what's going to happen. We don't have to guess how bright the bulbs will be. We can calculate it. Let's check out the results. All right, let's start with this series circuit, the single file line. Since the current has to push its way through both bulbs, the total opposition, the total resistance, just adds up. So 5 ohms plus another 5 ohms gives us a total of 10 ohms of resistance. Now let's pop that into Ohm's law. 1.5 volts divided by 10 ohms, that gives us a current of only 0.15 amps. That's half the flow we had with just one bulb. And the result? Both bulbs are going to be way dimmer. Okay, now for the parallel circuit. Brace yourself, because this is where it gets a little weird. By adding a second path for the electricity, you've actually made it easier for the current to flow. Think about it like opening a second checkout lane at the grocery store. The overall line moves faster. The total resistance of the whole circuit actually goes down. With two identical bulbs, it gets cut in half to just 2.5 ohms. So the total current being pulled from the battery is now 1.5 volts divided by 2.5 ohms, which is 0.6 amps, double what it was originally. That current then splits evenly, so each bulb gets its original 0.3 amps, and they both shine at full brightness.
This table really makes the pattern obvious. Look at the series column. As you add more bulbs, the total resistance just keeps climbing, and the current drops, making everything dimmer and dimmer. But in the parallel column, adding more bulbs actually makes the total resistance go down, which means the battery has to work harder and supply more and more total current to keep all those bulbs shining bright.
Now, our model, using Ohm's law, has been awesome for figuring all this out. It's incredibly powerful. But, it's important to remember that it's a simplified model. The real world always has a few extra wrinkles.
Just for fun, here are a couple of those wrinkles. For one, the battery itself isn't perfect. It has its own tiny bit of internal resistance. And what's really interesting is that a light bulb's resistance isn't actually a fixed number. As that little filament gets super hot and glows, its resistance actually goes up. But even with these little details, our simple model does a fantastic job of explaining what's going on. This whole journey is something you can totally explore for yourself with just a few cheap parts. But before you even think about doing that, let's cover the single most important part of this whole explainer: how to do it safely.
Okay, these rules are simple, but you gotta take them seriously. Number 1, never, ever short the battery. That means connecting the positive and negative ends directly with just a wire. It can get dangerously hot really fast. Because things can get warm, keep your experiments short and sweet. It should go without saying, but keep water far, far away from your circuits. And when you're all done, make sure you dispose of the batteries properly.
So let's just pause for a second and think about what we've learned. I hope one thing that's a lot clearer now is how one single, simple rule, voltage equals current times resistance, allowed us to go from just looking at a light bulb to predicting exactly how even more complicated circuits are going to behave. We went from a simple question to a powerful predictive tool. And I'll leave you with this final little puzzle to chew on. Every single light in your house, they're all wired in parallel. Think about it. You can turn on the kitchen light and it doesn't make the living room light get dimmer, right? They all shine at full brightness. Based on everything we just went over, can you explain why it has to be that way? Something to think about. Thanks for joining me on this one.